Okay, guys, so I want to talk about a web-based JavaScript app that we put together, me and Everton Darlan. My name is Dan Resnick, and this app is geared at helping us visualize Loci. Loci is a plural of locus, of triangle centers, of families of ellipse-inscribed triangles. Now this is going to become clear. The slides that I'm showing you guys here are available at this bit.ly address that I'm going to put on the description of the video. And the actual app itself can be accessed via this bit.ly address here. Okay, now what is this app about? Let's go ahead and head over to the app. So when you actually type in that bit.ly, it's going to expand out into this HTTP GitHub hosted application site, and the app just opens up that way, and it shows in this case here an ellipse, this white curve here, and a family. Let's stop this family. So it's always going to be a triangle family. Now it's going to be an ellipse mounted, or in this case ellipse inscribed family of triangles. Now the specific family that we're showing here is known as the three periodic or elliptic billiard family. Now, what's special about this family is that at any given configuration, the normal to the ellipse at each one of these three vertices bisects those two incident segments. Or in other words, if you actually shot a ray of light in this direction here, this ray of light would actually bounce off and reflect. If you imagine this ellipse as being internally mirrored, it would reflect and form a three-path that comes back to this location here. Now there's a lot of literature out there about elliptic billiards. I'm just gonna say or just outline a couple of properties here. There's something called Poncelet porism, which means that if you can actually find a path that does close, okay, you're gonna have a family of such paths. And if this path closes in n segments, you're gonna have a family of n segment paths. So I can actually hit on play here, and I can watch that family, the family of dashed triangles. Now they all have the sort of billiard property. They're all reflections at every vertex, and you get this one-dimensional family of triangles. Now a first question, oh yeah, before I forget, so this family, besides it being inscribed in an ellipse, it also circumscribes a fixed ellipse, which is confocal, which means to say it shares foci with the original ellipse. So the foci are shown here hidden, these two white dots. So if I change my aspect ratio, the ellipse aspect ratio, I can make it be closer to a circle. So you can see here the two foci, right? So the property of this family is that it's going to be simultaneously inscribed in the outer elliptic billiard and simultaneously exscribed or circumscribe a confocal caustic. Very well. Now, what does this web application intend to do? It tends to help us visualize triangle centers and the loci of these triangle centers. For example, let's take a well-known classical center of a triangle known as the incenter, x1. So the incenter of this triangle here, how is the incenter computed? If you could imagine in your mind's eye that you're extending the three normals, okay, and these three normals will intersect at a point known as the incenter. Now let me say something about this label x1. x1 in this notation, for example, if I use another classical center, the barycenter, it's known as x2, or the circumcenter known as x3. This notation actually comes from the Encyclopedia of Triangle Centers by Clark Kimberlin, and you can access it here at this address. And in this encyclopedia, believe it or not, there's about 40,000 catalog triangle centers. Actually, it seems like he expanded it and it's now reaching almost 50,000. Now the first part is the one I tend to hover more into, and that's called part 1. So if you click here, and that's the default, you're going to be on part 1 where you have 1,000 triangle centers listed. So if we start with beginning of the list, and there's a little bit of preamble here, But once you hit the very first cataloged triangle center, that's known as the incenter. Okay, and what this encyclopedia does, which is pretty cool, is actually gives you the so-called trilinear coordinates for this triangle center. It's barycentrics, and then it's going to list a bunch of properties that are related to the incenter. As you go down here, you're going to get into a list. But what I want you guys to focus on is if you go to the second center listed by Kimberly, that's x2, the centroid, or the barycenter. The third center, as you go down this list, is called the circumcenter, so that's x3, so forth and so on. So we're gonna adhere to this notation. Let's go back to our app, and now we're gonna go back here to the incenter, and by using my wheel on my mouse, I can zoom in and zoom out, and I can also vary the aspect ratio of my outer ellipse and just observe different families of three periodics. These triangles here are known as three periodics. Now, if I now make the system sweep this Poncelet elliptic billiard family, I can watch what happens to the incenter. And it turns out that the locus, this blue thing here, is an ellipse as well. Okay, so this is a really cool result. It has been proven by Olga Romaskevich. And this E here represents the fact that numerically the internal algorithm to this app is basically saying, yes, in fact, this path is an ellipse. Let's go up here to let's change this to 2, which is the centroid or the barycenter. It's also an E or ellipse. This E is also showing over here. Let's go to the circumcenter, x3, that's also an ellipse. Let's go to the orthocenter. There's an E there as well, so that's an ellipse. So if I vary my A over B, I can vary dimensions of this orthocenter locus, right? Let's go to the center of the 9-point center, which is x5. That's an E. Now I'm doing this because I wanted to get to x6. Let's see what happens to x6. This is called the sine-median point. Now notice that little e has disappeared from here. And here where I actually had an indication what kind of a conic it was, now I have an x, meaning I don't know what kind of a curve this is. It turns out this closely resembles an ellipse, but it's not an ellipse. It's actually a quartic. Okay, so if you exacerbate a little bit the A over B, you start getting a sense that this thing doesn't really look like an ellipse, but it's actually not easy to tell. Okay, so what this app allows us to do is actually to observe these loci. They're not always pretty like this. Okay, they can be more convoluted, but it also allows us to superpose one or more loci on top of each other. So for example, let's go back to the incenter here. I'm going to type 1. Okay, so there's the incenter ellipse. And I can say, okay, what if I wanted to superpose the barycenter? So I'm going to open up this quote-unquote second channel of our app. And now I can see both of them at the same time. Now I can also see that there are colors assigned to each one of them. So the locus of the incenter is assigned this color light blue or cyan. The locus of x2 is assigned this other color. I can change the color. I can say, okay, I don't like that. I want to make this guy be yellow. And I just do this, and now x2 is yellow. Okay? Or I can go back to the original, whatever it was before. It was something like that, magenta. So I can select which colors I'm going to use. And over the next few videos, I'm going to be going over many of the functionalities on this left area of the app, which you can explore. You can actually collapse it so that you get the full screen by hitting on this hamburger icon. You can go back up and show the interface back on. I can put a third locus here. Let's watch simultaneously the locus of the circumcenter and then the locus of the orthocenter. So there they are. Here I have now 4 loci simultaneously observed. Now because this figure is a little bit sort of vertical, let's rotate the whole thing 90 degrees. So I'm going to rotate it 90 degrees, and I can watch. Now my elliptic billiard is actually displayed with its major axis vertically, and I can better observe what happens. And there's so many things that are borne out by this. If I start changing my aspect ratio of the ellipse, you're going to get a lot of critical points. So for example, where the vertices of the x3 locus, and these four things are ellipses. You can see here the E, E, and E, and there's also markings here E, 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 and E. So there are four elliptic loci. So I can start studying and start calculating, what are the critical A over B's. And in all these simulations in this particular app, we assume B equals 1. So when you see here A over B, you're assuming that B equals 1, right? So looks like numerically at around 1.831, the locus of the circumcenter x3 touches the elliptic billiard internally, right? And there are many critical points like that. For example, I can also find the A over B for which a similar thing happens to the locus of x4. I can use my arrow keys here to be more precise. So that's happening at approximately 1.351. So I can get a pretty good understanding of not only the type of conics, if they're conics at all, of each one of these loci, but also their interrelations. Okay, so I'm gonna go back to that presentation. You can find this app at this particular bit.ly. Okay, and I'm gonna make a series of videos where I actually go over more and more of the functionalities available on this app.